In the last module, we have discussed that a mechanism is made of rigid bodies called links, and the relative motion between two links are constrained by joints. The joints may be 1 degree of freedom joints or 2 degree of freedom joints. Each rigid link has 3 degrees of freedom. So a natural question that arises is, what is the degree of freedom of a mechanism? In this part, we will discuss the answer to this question. Intuitively, degree of freedom of a mechanism is the number of inputs or independent parameters required to determine the position of all moving components relative to the ground. Now, the question of how we determine the position of all moving components given the degrees of freedom will be discussed in a later lecture. Over the next few slides, we want to answer the following question: how to compute the degree of freedom of a given mechanism. So our goal is the following: given a planar mechanism, determine M, the number of degrees of freedom. The degree of freedom of a mechanism M is the total number of degrees of freedom of all links minus the total number of constraints imposed by all joints. Now, any link in a plane has 3 degrees of freedom. We are given L links, and one of them is the ground link. So there are L minus 1 links that can move. So there are total 3 times L minus 1 degrees of freedom before the links are connected. Each 1 degree of freedom joint imposes 2 constraints. Therefore, if we have J1 1 degree of freedom joints, they impose 2 times J1 constraints. Similarly, each 2 degree of freedom joint imposes 1 constraint. Therefore, if we have J2 2 degree of freedom joints, then they impose J2 constraints. So 3L minus 1 is my total number of degrees of freedom, and 2J1 plus J2 is my total number of constraints. Therefore, what I have is M is equal to 3 times L minus 1 minus 2J1 minus J2. This is called Gruebler's equation with Kurzbach modification. And this is the equation that we will use to compute the degrees of freedom of any planar mechanism. So this reasoning allows us to develop a constructive method or procedure for computing the degrees of freedom of a mechanism. So what is the procedure? First, we will count and label all links, with the ground link labeled as link 1. Then we'll count the number of joints with 1 degree of freedom. Let's say it's J1. Then count the number of joints with 2 degrees of freedom. Let's say it's J2. And then once you have L, J1, J2, directly use Gruebler's equation to compute the degrees of freedom M. Now there are a few things that you have to be cautious about when you're using Gruebler's equation. The first thing is that there is only one ground link. You only count the ground once. All fixed links are considered to be one and the same ground link. The second point is links can have more than 2 nodes. So there can be ternary links, quaternary links, etc. The third point is that there could be joints each connecting more than 2 links, and these are called multiple joints. In case we have a multiple joint, we have to count the joint more than once. So the way we will count is the total number of links at the same joint minus 1. So let us elaborate on this a little bit more. So let us consider 3 links at one joint. So there's a revolute joint here, or a pin going through, and there are 3 links. Each one of the links can rotate with respect to each other or relative to each other. So let's say this is link 1, link 2, link 3. So let this angle be theta 1, 2, this angle be theta 2, 3. So this angle, the relative angle between 1 and 3 is theta 1, 3. So we know that theta 1, 3 is theta 1, 2 plus theta 2, 3. Therefore, if we just know these two angles, theta 1, 2 and theta 2, 3, we will know the third one. So although there are three possible angles, the degree of freedom is actually 2. Just knowing the angles between each pair of links is sufficient. So now what happens if you have n links? Let's draw a similar picture. So we'll have 1, 2, 3, this is n minus 1, n. So if I know the angles between the consecutive pairs, the angle between any two of them, like say 1 and n, can be computed by adding up all these pairwise angles. If we want to compute the angle between 2 and n minus 1, we compute 2, 3 plus 3, 4 plus up to n minus 1. How many angles are there? Independent angles. In this case, for every pair, there is 1. So there is 1 between 1 and 2, 1 between 2 and 3. There are a total of n minus 1 independent angles, where n is the number of links at this joint. Whenever you have more than 2 links connected at the same joint, which is called a multiple joint, the degree of freedom that you count there is the total number of links minus 1. Now let's go through some examples. So we'll start with the 4-bar example. First, we will use an intuitive approach to compute the degrees of freedom of this 4-bar mechanism, and then you will use Gruebler's equation, and you will see that they match. So a 4-bar linkage has 3 movable links, right? The links 2, 3 and 4 can move. The link 1 is fixed. So it is a total of 9 degrees of freedom, 3 times 3. Now there are 1, 2, 3, 4 revolute joints. Each one of these revolute joints imposes 2 constraints because it is a 1 degree of freedom joint. It allows 1 degree of freedom. So 4 revolute joints impose 8 constraints. So my degree of freedom of the 4-bar mechanism is 9 minus 8, which is 1. Now let's look at what you get using Gruebler's equation. Number of links are 4, so they are numbered. The ground is 1, this is 2, this is 3, and this is 4. Number of 1 degree of freedom joints we already counted as 4. Number of 2 degree of freedom joints is 0. So you substitute this in this formula, and if you do the arithmetic, you get 1. Note here that the ground link is a binary link. Now let's look at another example. First, we will count and label the number of links. The ground is labeled as link 1. Then we have labeled each one of these links as 2, 3, 4, 5, 6, 7. And this slider here is the link 8. How many joints are there? Let's count. 1, 2, 3, 4, 5, 6. There is a pin joint between the slider 8 and link 7, so that would be the 7th joint. There is a sliding joint between the slider and the ground, or a prismatic joint between the slider and the ground, so that would be joint 8. Now let's come here. This is a multiple joint. There are 3 links that are connected to this multiple joint. So we will count 2 joints here, joint 9 and 10. So our number of links are 8, number of joints, 1 degree of freedom joints, are 10. There are no 2 degrees of freedom joints here. So if I substitute L equal to 8, J1 equal to 10 and J2 equal to 0 in Gruebler's equation, and do the arithmetic, I get M equal to 1. So the degrees of freedom of this complicated mechanism is 1. Let's go through another example. Again, we will first count the number of links. Ground is labeled 1, 2, 3, 4, 5, and 6. So we have 6 links here. How many 1 degree of freedom joints do we have? 1, 2, 3, 4, 5. We have a multiple joint here, and there are 3 links, so this will count as 2. So 6, 7. So we have 7 1 degree of freedom joints. How many 2 degrees of freedom joint do we have? This joint here is a 2 DOF joint, or 2 degree of freedom joint. Why? Because when you think about the degrees of freedom between two bodies, one good way to think about it is to just take the two bodies in isolation. So here I have this body here and I have the ground. Since this body is curved, it can rock back and forth, and it can also slide. So there are 2 degrees of freedom. That's why this joint here is a 2 degree of freedom joint. So just to write it all out, L equal to 6, J1 7, J2 1, and we put it in the Gruebler's equation, and we see that the degrees of freedom is equal to 0. So what does it mean to have degrees of freedom equal to 0? It means that it is a static structure. This cannot move. So Gruebler's equation actually tells us that if my degree of freedom is greater than 0, then I have a mechanism and the links will have relative motion. If the degrees of freedom is equal to 0, then I have a structure and there is no relative motion possible. If my degrees of freedom is less than 0, then I have a preloaded structure. Not only there is no relative motion possible, but there may be some stress present at the time of assembly. So it's also called a preloaded structure. So if you look at the figure here, the figure A is the simple 4-bar mechanism with pin joints, which is a 1 degree of freedom mechanism. Now, if I just take 3 bars and pin joints, it's a structure. There are no degrees of freedom. If I take 2 bars, one curved, another straight, and join them, we have a preloaded structure. Because the degree of freedom, if you compute it, will be -1. And I'm leaving it as an exercise that you can compute the degrees of freedom of the triangle and this 2-link mechanism here. So let's go through another example. So what do we have to do first? We have to first count the number of links. So the ground is 1. Let's call this slider 2, 3, 4. Let's call this link 5, link 6, link 7, link 8, link 9. So I have 9 links. How many 1 degree of freedom joints do I have? 1 revolute here, 2, 3, 4, 5, 6, 7, 8, a sliding joint here between the slider and the ground, that is 9, sliding or prismatic joint, that's 9. And here I have a multi-joint between link 5, 6 and the slider. So there are 3 links here. So I will count 2 joints, that is 10 and 11. I have 9 links, including the ground, 11 1 degree of freedom joints. There are no 2 degree of freedom joints. So if I just put it in the Gruebler's criteria or Gruebler's equation, I get the degrees of freedom as 2. Now one thing that you should understand in the derivation of the Gruebler's equation, we didn't really assume anything except for the degrees of freedom of the joint and the number of links, not the shape of the links, nothing else. So this is quite powerful and general, but this also has some problems, as you will see in the next few slides. So the question is that, does Gruebler's equation always give us the right result? The answer, unfortunately, is no. Sometimes it can lead to results that are incorrect, and these are called paradoxes. So let's go through them in a little bit more detail to understand them. So let's first look at this mechanism on the top here. How many links do we have? We have one ground, then 2, 3, 4, 5 links. Okay, so L equal to 5. How many 1 degree of freedom joints do we have? 1, 2, 3, 4, 5, 6. So we have J1 is equal to 6. There are no 2 degree of freedom joints, so J2 equal to 0. If I substitute L, J1 and J2 in Gruebler's equation, I get the degrees of freedom as 0, which is correct for this mechanism. However, if you look at the second figure here, there is no difference between these two mechanisms in terms of the number of links, number of 1 degree of freedom joints, and number of 2 degrees of freedom joints. They are identical. The only difference is in the link lengths. This mechanism here can have a rotational motion. It's not a 0 degree of freedom mechanism. It is a 1 degree of freedom mechanism. So there is a paradox there. If you do the calculation, you will get 0, but actually it has a 1 degree of freedom motion. Now let's look at these two cylinders. The two cylinders touch each other and there is a frictional contact here. And the friction is such that there is pure rolling and no slip. So how many links are there? The ground is 1, this cylinder is 2, the other cylinder is 3. So there are 3 links. How many joints are there? This is one joint, revolute joint. This is second revolute joint. And there is a 1 degree of freedom joint here because it allows only rolling and no slipping. If slipping were allowed, the degrees of freedom at this joint would be 2. This is the third joint. So I have J1 equal to 3 and J2 is equal to 0. So if I substitute L and J1 and J2, so J2 is equal to 0. In the Gruebler's equation, I get the degrees of freedom equal to 0. But we know that if this cylinder rotates, this one rotates in the other direction. So we know that cylinders can move relative to each other. So what's happening here? Why do we get these paradoxes? And it's specifically because Gruebler's equation pays no attention to link sizes or shapes. So when there are unique geometric configurations, it can give misleading results. Let's consider another example where Gruebler's equation may give misleading results. Let's consider the mechanism here. How many links do we have? The links are marked out. The ground is 1. This is the link 2, link 3, and link 4, which is the roller here. How many joints do we have? 1 revolute joint here, second revolute joint here. There is a third revolute joint here. So that's 3 1 degree of freedom joints. This joint here is a 2 degree of freedom joint because it allows both rolling and sliding. So we have L equal to 4, J1 equal to 3, and J2 equal to 1. If we use Gruebler's equation, our degrees of freedom 2. However, there is a passive or redundant degree of freedom here, which does not alter the constraint between this input here and this output. And what is that redundant degree of freedom? This rotation of this roller. This roller can rotate without affecting the output. So the actual degree of freedom in this case is 1.